Hey everybody, I'm Brian Swingle, and this is a video abstract for our paper titled Approximate Quantum Codes from Long Wormholes. I wrote this paper with my wonderful collaborators Greg and Fook almost 2 years ago, and you can find links to the paper and to a longer talk in the description. The broad context is quantum error correction, which is crucially important for building large-scale quantum computers. Quantum error correction also offers concepts and tools that have proven useful in other parts of physics. For example, in topological phases of matter and quantum gravity. Here we go in a different direction by using ideas from many-body physics and quantum gravity to elucidate new kinds of quantum codes. We study the approximate ground spaces of the Sachdevier-Kitaev model and its low-rank cousins as approximate quantum codes. The ground state entropy per particle translates into the rate of the code, and we show that our codes are constant rate. This means that the amount of encoded information is proportional to the total number of degrees of freedom. To define and study a notion of code distance, we turn to a mutual information-based quantity, which reduces to the usual notion of code distance for an exact code. Roughly speaking, the code distance measures how many simple operations, like bit flips, are needed to go from one code state to another. We compute the code distance and show that it can be made quite large, almost proportional to the number of degrees of freedom. We also give a novel geometrical interpretation of the code distance for our codes. The physical errors live at one end of an emergent holographic wormhole, and the encoded information lives at the other end. In this picture, the large physical distance along this emergent wormhole translates into a large code distance in the code. We can compute all this using tools of holographic duality. This includes calculating correlations, as well as the mutual information quantity of most interest. And with these tools, we can show that when the wormhole is long, the mutual information becomes small, and thus the code distance becomes large. Now, while the codes we consider have quite good properties in terms of rate and distance, they aren't yet useful for building quantum computers. For example, although we have some preliminary ideas about how to encode information in these codes, decoding them may be more challenging. Nevertheless, these codes significantly broaden the horizon of what is achievable with approximate quantum error correction, and they contribute to the ongoing rich exchange between physics and error correction. For example, these codes shed new light on a version of the no low-energy trivial states property and its relation to many-body systems and their code properties. So thanks for listening, and enjoy the paper.